Hello, I'm David. It's semester 1, 2025, and this is a revision seminar for Algebra 2. Last one at the University of Adelaide. How exciting and sad, but who knows. Anyway, hello, those watching this online. I've already said hello to these people. And that's enough of that, and I'll put my screen back on. Okay. So I've been given some requests, and my two requests are about the two preferred ones are about the isomorphism theorems and duality. So let's okay. So I helpfully had the textbook on someone's laptop here. So isomorphism theorems are about the behavior of quotient groups and homomorphisms between groups. And so it seems reasonable that I should write down what those things mean before I start that. So phi, which sends one group to another group. So this is a definition, right? This is my memory of the definition, and then you can all check if I've got it right. So this is a homomorphism when phi of G1 times G2 is the same as phi of G1 times phi of G2. For all G1 and G2 in the domain group. Okay, and this multiplication is the operation in G, and this multiplication is the operation in H. Okay, so that's the definition of a homomorphism, and an isomorphism will be one-to-one and onto, or in fancy words, surjective and injective and surjective, or bijective. Do they use those words in this course? Bloody Babaki. Sorry. And so definition. And it's a homomorphism, and it's bijective. Okay, sweet. And you would normally write that G is isomorphic to H, right? Well, wait, we're not up to that yet. When Neil, just wait. And then you'd write G. It's a single, no, double equals, cool. G is isomorphic, and you'd say G is isomorphic to H. Sorry, thank you. Cool. And you'd feel that these two groups are actually the same group, just written with different symbols. Okay. Cool. So their operations work the same way, and they're the same size. So that's basically it. They're the same group. Right. So the isomorphism theorem mentions these two things called the kernel and the image. So we need definitions for those as well. So the kernel of phi and the image of phi. Okay, so this one isn't really restricted to group things. The image of any function is just a set of its outputs. And so that's true not just for homomorphisms, but for all functions of any kind, anywhere. So this is so that's the set of phi of G such that G is in G, like that. And the kernel is the inputs that go to the identity. Set of phi, no, the set of G's in G such that phi of G is the, do they use E for the identity? In H. So when you first learned the word kernel here at University of Adelaide, you learned it in Maths 1B. And in that case, the identity of the target group was the zero vector. So the kernel is the zeros of the function. It's the things that arrive at zero. But if your group is a multiplication group, it's the things that arrive at one. But whatever the identity is, the things that arrive there. But it's borrowed from an idea of going to zero for an adclip group. And it's really important in my mind to remind myself that the kernel is inside G and the image is inside H. So the picture in my head is this, is that here's G and here's H. And there's phi. And the kernel's in here. And the image is in here. Yeah. So they're in different places. And what in fact happens is that everything in G ends up somewhere in the image. And so there may be a part of H that just doesn't, nothing arrives there. And all the things that are in the kernel end up at the identity. Like that. So that's the picture in my head of how these things work. But I will have to adjust that picture in order to draw the isomorphism theorem. Yeah. Has your lecturer attempted to draw the isomorphism theorems? Or in the textbook? No. Oh, for this. Okay. Sorry. Okay. But that's what it is. And then the isomorphism. Now, I think we have all of the bits of notation that are in the isomorphism theorem other than quotient groups. Yay. That's also a piece of notation in the isomorphism theorem. So I'm just going to make sure I understand that. So a quotient group, I will use not H because we've already used H for the output. So maybe I'll use F. So quotient group goes that if F is a normal subgroup of G, then GF is the group whose elements are the cosets of F in G. Is that right? Cosets of F in G. So i.e. the set of GF, such like that. Is that right? The quotient group is made of cosets. Yep, and multiplication in here and the operation is that if you have G1F, G2F, then what you get is G1, G2F. Is that right? Cool. Okay. Yes, so we should probably write that down too. So yeah, you can say just the cosets in this context because the left cosets and the right cosets are the same thing. But the definition, normal subgroup. So F is a normal subgroup of G, and which you write as F like that. Is that right? With a triangle? So without the equal, it's properly smaller than F then, G then? Okay. We write that. So F is a normal subgroup of G, and you write that. So what that means is that F is a subgroup, which means it's self-contained under the group operations of the operation and inversion. And GF is FG for all G, yep. I left cosets equals right coset. Okay, for all the cosets. And that allows us to actually make it possible to do this and make it a group. So if you attempt to make this thing, because technically you could make this object, it just won't be a group unless F is a normal subgroup. Or well, so multiplication won't be well defined. It'll just be ridiculous. Okay, so that's all the, wow. So that is all of the notation in the first isomorphism theorem. No wonder it's a curly one. So you have to understand all of those things before you can understand the notation in the isomorphism theorem. Okay, cool. Right. I do just want to draw a little picture of. Do I want to draw a picture of cosets? Give me a second. Oh, so just a thing about the way cosets work that I just need to remind myself of is that this is true here, but you could also just as easily do it as like F is like G inverse FG for all G and G. That's an alternative, but you could do instead. Yeah. And there's a theorem probably that says that all of these things are equivalent to being at normal. Does that sound like a theorem that existed somewhere in the course? Yeah, anyway. Because technically you just need that G inverse FG is just inside F. It doesn't have to, like, it'll work anyways. Well, maybe that only applies to finite groups. Anyway, this will do. You can look that up later. And the interesting thing about groups with cosets is that it's easier to draw them as rectangles. So this is G and this is F, and there's the identity of G there, which is definitely inside F. Then when you make the cosets, they'll tend to divide G into stripes. So these are all the elements of F, and then you multiply them all by G, and so you'll get like G1F, and this will be like G2F, and this will be like G3F, like that. And so when you multiply all of these by G, you'll get that. Well, G1, all these by G2, you'll get that. And then it turns out that the element G1 is definitely in this one, and the element G2 is definitely in this one, and the element G3 is definitely in this one. And so you're yeah, and so this group here of the cosets, when you multiply two of them together, it'll produce one of the other ones, and whatever. But I find it useful to think about it this way. But if it wasn't normal, then the opposite cosets would probably be sets that go in a different direction. But a normal subgroup, the cosets are G1F is the same as FG1. So there's two ways to not be normal. One of them is that for the cosets don't match up, G1F is one of the right cosets, but not the same one. And the other one is for them to like not line up at all. So this will be there, but the rest of them will like be little weird pieces the other way. So yeah, so that's my illustration of what that looks like. And then the isomorphism theorem, we're nearly there. The isomorphism theorem says, and what does it say? I'm going to read it from the textbook. The first isomorphism theorem. Ominous that it's the first one. So the first isomorphism theorem says that if phi, which sends G to H, is a homomorphism between groups, then the kernel of phi is a normal subgroup of G, and the factor group G factored out, factor group G over curve phi is isomorphic to the image of phi, which is interesting because that would seem to suggest I wouldn't be able to write this at all unless curve phi and im phi were groups. And so that must mean that there's a theorem somewhere or a lemma or something like the zeroth isomorphism theorem, but there's a theorem that says that the kernel of a homomorphism is a group. And the image of an homomorphism is also a group. So this is a group. So that is interesting because we wouldn't be able to write this statement unless that was true. So we've got a bonus extra theorem here, which so it implies that these two things must be groups. I mean, it's obviously a group because it's a normal subgroup, but that's also a group there. Okay, I'm going to draw a picture of this. So here's G. And here's H. And there's a homomorphism between them, right? And I'm going to draw the image of G like this, image of phi here. There's a good reason I've drawn it that way instead of vertical. Okay. And then the kernel of phi, I'm going to draw like this. And that will all end up here at the identity. Okay. And then what we're saying is that when you quotient G with the image of phi, then what you get is something that is isomorphic to the image of phi. Sorry, quotient G with the kernel of phi, what you get is something that's isomorphic to the image of phi. So what I'm going to do here is in fact this. 1, 2, 3. Like that. And I'm not even going to do that. I'm just going to put a single dot there. Okay, that's my picture. So this has like probably several things in it. is the finite group, and EG is one of these. Thank you for bearing with me as I adjust my diagram. Okay, so all of these elements end up here at the identity. All of these elements end up here. 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 And what happens is that the various elements of the image of phi end up being, each of them is the image of one of the cosets. That's how that works. So each element of image phi is the image of one coset of kerr phi. And that's why they're isomorphic, because this thing is, each of them gets an entire coset. That's the idea. And so multiplying two of these is the same as multiplying the matching two of these. That's how the isomorphism works. Wait, I'm just looking at what the second one is. Oh, okay. Oh, just calling it first just made me wonder what the other one was, but they didn't cover the second one. Sorry? Okay. Oh, wow. Yeah, I've never seen that in my life. Okay, so it would seem, yes? No. You don't need H to be bigger than G, because it's totally possible for this to actually be a one-to-one thing, and H could be smaller than G. So no. H is great, the size of H is greater than or equal to the size of G. Yeah, H doesn't have to be bigger than G. Totally can. It's just that if H is smaller than G, then the homomorphism is simpler, like everything goes to the same place or something. So it is totally possible for H to be smaller than G. It's just you get bigger cosets over here. Because no. Yep. The bijection is between these cosets and these ones here. Just the ones in the image. So it's totally possible for there to be plenty of things in H that aren't even in the image. So H can be big as you want. But it's also totally possible for H to be smaller than G and just end up with only two cosets here because there's only 2 points here. So yeah, if H is smaller, the cosets are bigger. There's less cosets, yeah. So the smaller H is, the fewer cosets there can be, which makes the cosets bigger. Yeah. Yeah. So so here's an example. If you take any group and you have a homomorphism into this set, which is just 0 and 1, like into Z2, is that how they write this? Z2 under addition. Then what that means is that as long as you get both of these answers, so if there's a phi here that's onto, then what that means is over here there will be 2 cosets because there's only 2 elements here. And you'll get the kernel of phi and everything else that isn't in the kernel will end up there. And so this one will go there, and this one will go there. Welcome. So it would be really cool if we could have some sort of example of trying to do something with this rather than me talking in generics. Yeah, because our request about the isomorphism theorem was, let me just check that's not my computer at all. Let me just check my email. Don't really want all my emails on the video recording. You can see them, but I don't need them on the recording for the world to see. Nope, that's fine. Okay. Do we have any problems from workshops or something? Presumably there's exercises in this textbook. Oh, I should just say, just before I do this, that this is an isomorphism. These being isomorphic means there is an isomorphism, and the isomorphism is psi probably psi of G cur phi is phi of G. Yep. Yeah. So that's isomorphism stuff. Isomorphism. Ah. Trying to find one that seemed to be about the isomorphism theorem. Ugh. None of them feel like they're about the isomorphism theorem. I don't really understand. Bear with me. But there's lots of questions about whether things are isomorphic or not, which is these questions here. Yeah. Okay. Yes, that might be more appropriate. Mm-hmm. Okay. Oh, question 8 looks fun. Okay. Well, I'm going to write down question 5 here. Well, what's this from? From chapter whatever?
It's not from the knowledge.
Oh, okay, that's fine. Do you know what the U stands for? Well, I just said is this a notation for the type of group? Oh, the ones that have, yep, the ones that have multiplicative inverses.
Yeah, it was in workshop
Okay. And this is a group under multiplication, not addition. Yes, it is. Because it doesn't include zero. So it can't be an addition group, or it would need zero in it to be the identity. Ah, cool. So U30, therefore, just to be sure, U30 will have 1 and not 2 and not 3, but it will have, no, it will not have 4. It won't have 5, it won't have 6, it will have 7. It won't have 8 or 9 or 10. It will have 11. It won't have 12. It will have 13. It won't have 14 or 15 or 16. It will have 17. It won't have 18. It will have 19. It won't have 20. It won't have 21. Won't have 22. It will have 23, but basically the prime numbers. 23. It won't have 24 or 25 or 26 or 27 or 28, but it will have 29. Okay. Wow. So pretty much the prime numbers, but the things that aren't multiples of 2 or 3, or 5. Yeah. Okay. And apparently 111 is a subgroup. I just want to be sure of this, just to be clear. So 11 times 11 in Z30 would be 121, which is 1 mod 30. Awesome. Yes. Okay. Cool. And 1 times 1 is 1. But okay. And so we want the cosets. Right. So 1, 2, 3, 4, 5, 6, 7, 8. There'll be 4 cosets. Because this has got 2 in it, and so we'll be cutting this into pieces of size 2. So we've already got 11 in this coset, so we have 7H. Will be 7, and 7 times 11 is 77, which is 17 mod 30. So we'll take off 60. Okay, 7 and 17. And so that's dealt with those two. And then 13 times 8. 143, which is 23 mod 30. And the 19 and 29 must be the other ones. Cool. They are the 4 cosets. So, I could theoretically define if I happen to think of a homomorphism that sent this group to some other group of size 4, then this would be isomorphic to that. Interesting. So just a second. So just to check, I wonder if this is a normal subgroup. It is, because this is an abelian group. So it's automatically normal. Okay, good. Excellent. Okay, so abelian groups automatically, all of their subgroups are normal. Okay. Cool. So I just want to check something. So 7 times 13 would be 91. Is that right? Which is 1. And so these two are inverses. And so 19 would have to be its own inverse. Yeah? So 19 times 19. Yeah, it is. Cool. So yeah, because I've got 400 minus 40, which is 360, which is a multiple of 30, and so there's a plus 1 left over. Okay. So this one's its own inverse. So the way that this group works is that you have these two inverses of each other, and this one's its own inverse. So there are only 2 groups of order 4, as far as I know. Is that right? So one of them, everything has order 2, and the other one is this one. Okay, just thinking it through. Wow. So this is the Klein 4 group then. Like these are the 2 rotation. No, everything in the Klein 4 group has order 2. It's the other one. D4. Oh, crap. I keep forgetting. What are the groups of order 4? There's the one that's the symmetries of a rectangle, right? And it's made of a 180-degree rotation. And then 2 reflections. Yeah, so but for a square, there's more rotations. Like for a rectangle, there's only 1 rotation because you can't rotate at 90 degrees and it'd be the same, like a proper rectangle that's not a square. What's that? What was the S? Oh, what's the other flip? Oh, that'd be SR, wouldn't it? Like that. Because if you flip and then rotate. This is the 180-degree rotation. Well, what's the vertical one then? What's the flip this way? Is that S times R? Must be, because it couldn't be anything else, could it? And this was the reflection, right? This way. And this is apparently the reflection this way. So just thinking it through, I'm just going to pause and think about some of the basics of groups. Because this is a permutation group ultimately, and so you've got the identity, and you've got 1 switches with 4 and 2 switches with 3. That's this one, and then you've got this rotation, and so we do 180-degree rotation, which means that the 1 goes to 3 and 2 goes to 4. And then we have the other row, the other reflection, which should be 1, 2, and 3, 4, right? That should be this entire group as permutations. And presumably, when I multiply these 2 together, I should get that one. So come in, 1 doesn't change, it becomes 3, and then it becomes 2. And then come in, 2 becomes 4. And then 4 becomes 1. Okay, that's cool. and then 3 becomes 1, and then it becomes 4, and then 4 becomes 2, and then it becomes 3. Cool. Okay. Just checking. Everyone okay with permutation multiplication? I just wanted to check. I know this group as V4. Nope, D4 is the one for the square. Like D4 has 8 elements, because this will have E and the reflection and R squared and R cubed and SR squared and SR cubed. Yeah, okay. And if you look at this, you've got this subgroup, and it has 2 cosets. Like, sorry, it has, so you've got this subgroup, has 2 cosets, but you also have this subgroup, which has 4 cosets. Yeah, okay, just working my way through it, just making sure I've got it right. Okay. And presumably there's other subgroups, but these are the classic ones. So this one's the rotations, right? And so you've got all the rotations, and they can be offset by a reflection. Okay, cool. So I have a question. Is this group isomorphic to this group? So we can make U30 factoring out 1 and 11, right? That group, is it isomorphic to this group? Why not?
I guess because the Irish alphabet stuff and one random this. After the first one, yeah, third one.
Yep.
Oh.
And so there's lots of ways of showing that it's not, but this is not so it's isomorphic to this, just to check. And this is not isomorphic to the U30 over 111, because everything in this group has order 2. Like everything here is its own inverse. But in this one, neither of these were their own inverse. So that's a different group. They can't be isomorphic because it doesn't preserve inversion. Yeah. And as you said, like when you multiplied these two, you got the identity. But when I multiply these two, I get the other one. And so that's not going to be a, and if I multiply these two, I get the other one. So with this one, any two of them, if I multiply that aren't the identity, if I multiply them, I get the other one. Whereas in this one, when I multiply 2 of them, I get the identity. So anything that doesn't match between the 2 of them and the way that the multiplication works is a proof that they're not isomorphic. What is isomorphic? Is there anything that, because there's another group of order 2, of order 4, sorry? Yeah, there's Z, cool. Actually, I think there might be, yeah. So Z4 on the other hand, like that, under addition. Yeah, look at that. So 1 plus 3 is 0, and 2 plus 2 is 0. 2 is its own inverse, 1 and 3 are each other's inverse. That's the same shape as this one. And so you could make an isomorphism that went from G3111. Sorry? Oh, U, sorry. Yep. From U3111 to Z4 by phi of 1. Phi of 111 will be 0. And phi of 2 of 19H. Sorry, I should just call it H. Phi of H is 0. Phi of 19H is 2, because that's the one that was its own inverse. And these ones could be whichever way around we like. So I could call this one 3, 1, and this one 3. And that would be a perfectly good isomorphism. Wow! Chair went down. Yeah, that would be a perfectly good isomorphism. And we just want to be absolutely certain that it really works. Phi of 7H, 13H is phi of H, because we just figured out earlier that 13H times 7H was H. And that is 0. And phi of 7H plus phi of 13H, because the operation in Z4 is a plus. And that would be phi of, that would be 1 plus 3, 0. That's pretty cool. So that definitely works. What about one more test? Phi of 19H times 7H. So 19 times 7 would be 20 times 7 minus 7. So that would be 133. And that'd be 13. And 5 19H plus 5 7H is 2 plus 1, which is 3. Cool. I mean, you have to check all the combinations technically. Yay. Okay. Wow. That was interesting. Whole lot of weirdness happening there. I don't think I've ever seen the notation U whatever. That's new this year. Okay. Right. One last one. Ready? I've now got it. Yep. Do I really want to do this? Do I really want to do this? Yeah, I should just stop. Yep. This should be allow me to make the isomorphism theorem. If I made a homomorphism that only produced even numbers, because the even numbers are isomorphic to Z4, and such that its kernel was only 111, then that would match up with this thing. So it should be possible. It should be possible to set it up so that the image was this, which is isomorphic to Z4. And the kernel is this. because then you would have that U30 divided by the kernel. Sorry, factored out, the kernel is isomorphic to the image, which is Z4. It should be possible to set that up based on the homomorphism theorem and based on what shape we know this is. And this group can be found inside Z8 as the even numbers. So it should totally be possible to set up something that only sends 0 and 11 to 0, and everything else is sent to only even numbers. I cannot think of one at this time, but it's going to play on my mind for weeks probably. I've already got something else on my mind that that's preventing me from doing the work I should be doing. But here we go. That's fine. So I don't know, that's not necessarily a good example. It's just what's on my mind, because the isomorphism theorem doesn't officially work the other way, but it technically should be able to. Like if you find a quotient group and you find that it's isomorphic to a subgroup of another group, it should be possible to set up a homomorphism from one to the other so that the kernel is the thing you factored out and the image is the thing that it arrived at. Yeah. Yeah, I think that there's like one of the later isomorphism theorems is that it works the other way. But anyway, that should totally be possible. Thank you for letting me work through that. I hope it was helpful to see me do that, because I certainly understand a lot more than I used to, having thought about all of those individual groups. Right. Okay. So yeah, technically to make it a homomorphism, you would have to check all all 6 combinations to make sure they all work. Yeah. Okay. All right. Do we want to try and talk about duality? All right. Is there a separate textbook for the other bit?
No.
Okay. I'm going to write down the definition of dual space and do what we did before and try and come back and figure out what all the other bits of things that go into that are. Okay. So this isn't a linear algebra thing. You've got to love the self-assuredness to call your book done right. I wonder what their metric for correctness is. Because is it based on understandability by the student, or is it based on some other idea of what linear algebra is supposed to be like?
I think their main point was to determine intuitive, and we should use them first because that.
There's a point at which I think things naturally produce determinants, but anyway. I do understand. I understand determinants like no one needs it. That's all right. Historically, determinants were invented before linear transformations and matrices, and so there's no reason to have them in linear transformations and matrices other than historical. But I still like the idea that matrices only exist because of determinants, and so it's kind of historically. Anyway, that's okay. To be fair, even if you believed in determinants, they don't come into formal abstract linear algebra very often anyway, even if you did believe in them. Okay, cool. But it's still very self-assured to call it that. The dual, so we've got a vector space V over, there has to be a field, right? Do they do it with a double struct F on paper? It's in bold in the book. I'll do it that way. There are two choices for how to write bold on paper. One is to underline it and the other one is to double strike it. But double strike seems right in this context. Okay, vector space over a field F, right? And then the dual space is the vector space of linear functionals. Right, slower, David. Linear functionals on V. Okay, so linear functionals. So the vector space of linear functionals on V, and there's a notation here. V dash is the dual space of V, and the linear functionals is this. What an interesting ballad. Okay. So right. So this is setting up linear functionals from scratch. But if I didn't want to write all of that, I could just write V dash. Apparently. And the linear functionals are a linear map from V to F. Which is what this statement here is. Okay. So this isn't technically the set of linear, oh, I see. This notation is the set of linear maps from V to F. And we have redefined, we've got a new name and said that thing is called a linear function. Those things are called linear functionals. So just to be, just wait. Okay. So this from V to W is the set of linear maps from V to W. Yeah. The set of, do they use phi? Yeah. So the set of phi, which sends V to W such that phi is linear. Right? Where by linear we mean that phi of V plus W is phi of V plus phi of W. Damn it. I don't like the curly phi. And phi of KV is K phi of V, right? Okay, cool. And so, yep, right. So linear maps from V to W. Okay, cool, cool, cool. That's what that is. And then these go from B to F. That's just phi is linear. Right, and so that's the same rules. But the interesting thing is that in this one, you're going to a field anyway. And so this scalar multiplication here is just ordinary multiplication. That's the difference. Okay. Cool, 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 cool. Right. So just as an example, so this would contain, for example, phi of x, y, z is x plus 3y minus z. That's a perfectly good linear map from the R3 to R. Okay, cool, cool, cool. Just checking. And in fact, they'd all look like that, just with different coefficients. So it would be like, they'd all be something like phi of x, y, z is like ax plus by plus cz for some a, b, and c. They'd all look like that somehow. Okay, a, b, c. Okay, which, interestingly, means that every one of these things has 3 coefficients. And so that means it's the same size as R3. The collection of linear maps is described by 3 real numbers in the same way as the vectors in R3 are described by 3 real numbers. So it's the same size as R3. And the theorem probably says that it's isomorphic to R3. In fact, the first theorem, blue is apparently theorem. The first theorem is that the dimension of V dashed is the same as the dimension of V, meaning it takes the same number of basis vectors. But let's be clear, basis vectors are just ways of setting up coordinates. So it requires the same number of coordinates to describe every one of the points in it. Okay, cool, 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 cool. So it's useful to have an archetype like R3. The linear maps in R3 are all, can I just be even more? Watch this. This is the dot product of these two things. And so these vectors describe completely the linear functionals on R3. And that's why they're isomorphic to R3. Yeah. Even better, we could write it as this is a row and this is a column. So R3 is like column vectors and the linear functionals are row vectors. Yeah. Cool, huh? And I think it's not too bad to think about them that way, to think about one of them as the original one as column vectors and the other one as row vectors, because transposing is kind of equivalent to adjointing. I don't know if you did adjoints in this. They only kind of put adjoints in this course like every second year, and so I just lost that. I'm still not big on that. I can't remember all the details, but yeah. And in MATLAB, if you want to transpose something, you put a dash on it. So V dashed would be the transpose of V if V was a matrix in MATLAB, and so that matches with this too. So anyway, cool. So that's what it looks like with vectors. And so with traditional vectors of the type that you saw in Maths 1B, it's pretty simple. It's like, well, there they are. But one of the purposes of abstract algebra is to do it on things that aren't R3, or at least don't look like R3 from at first glance. And so you have to have all this practice at figuring out how to deal with this on things that don't look like R3. But the idea is that you can rewrite it to be more or less this if you want. Because you know how when you did linear transformations from one vector space to another, you could, if you concentrated and used a basis, write them using matrices. You get a matrix for the linear transformation relative to a particular basis. We did that in this course, right? No? Yes? Yeah, but also just not even change of basis, but the linear transformation from one place to another can be written as a matrix as well. And that's the similar vibe. Okay, so just right. So that's the dual space. When people are thinking duality and thinking, gosh, I'd like someone to explain that to me, what are they wanting? Are there bits of dealing with duality in assignment or in assignment questions that have bothered people or workshops or things? Oh, it's this whole dual basis thing, isn't it? That's the thing. Okay. That's okay. Sorry?
This yeah, change of basis before dual basis. Yeah.
Oh, and then we have dual. Oh, for the sake of it. Okay. The notation just gets very dense, where each symbol has a lot of meaning behind it. That's okay. Okay. That's all right. We're fine. I just want to do another example before I do this of linear functionals. One of your classic vector spaces that tends to provide examples in a course like this is the polynomials of a certain degree, well, up to a certain degree. Is there a notation for what that is?
Like a subscript.
Okay. So we have curly P like 3, and then with an R, and that would be the polynomials up to 3, right? With coefficients from R, right? That's what it is. Yeah. Okay, cool. In particular, they are functions. So they are a vector space. And there are linear things you can do to set things, to functions like this, that will turn a polynomial into a real number. So a linear functional turns a polynomial into a number. And there are several things that you're familiar with doing to functions that produce numbers. And they are all, coincidentally, linear functionals. So, for example, the linear functional, which when you do a polynomial, subs in 3 is a linear. The action the action you perform on a polynomial px, which subs 3 into that polynomial, that is a linear function. So this takes a polynomial and produces a number by subbing 3 in, or 4 or -1 or whatever you want. So this is the action. The action of subbing in 3 is a linear functional. Because if I add 2 polynomials first and then sub in 3, it's the same answer as if I sub in 3 and then add them. And it works for the multiplication as well. So that's one of them. Also a linear functional. This takes a polynomial and produces a number by doing the integral from one place to another. And you could, if you wanted to, change these limits to whatever you wanted, and it would still be fine. It would still work as a linear function. So the action of doing definite integral in the interval from 0 to 2. That's a linear functional as well. And finally, you can combine things by combining either of these with multiplying by a constant. Now, multiplying by a constant is not a linear function. It's a linear transformation from P3 to P3, multiplying by a constant. But if you do that and then a linear transformation will do the same thing. So the classic, so you could do this. That would work too. Subbing in 3 and then timesing by 5, still a linear function. That will work fine. And the last one I want to do also a linear functional. Because differentiation is a linear transformation from P3 to P3, actually from P3 to P2, but whatever. And then subbing in 0 is a linear transformation, is a linear function. And so most of the processes that you're familiar with that turn a function into a number are linear functionals. Integration and differentiation, as long as you produce a number at the end, then you get a linear functional from that process. Which is kind of cool, actually, to me. Yep. Yep, absolutely. So, like that. So if you differentiate as many times as the degree, technically that'll be n factorial times the, yep, so you could do, for example, that's great too. You could just take out the constant term. That'll work just as well. In fact, you could have phi of px to be the x cubed coefficient. That will also be a linear functional too. Because if you add 2 polynomials and find their x cubed coefficient, that's the same as finding the x cubed coefficients first and then adding them. So like this is, I just find this hilarious to me. Like there's all these things that you could naturally just do to a polynomial and to produce a number, and they're all linear. But what does that mean? Well, the thing is, the linear functionals are a vector space of their own. That's important. So, and being a vector space, they have a basis of their own. I mean, not all vector spaces have vector spaces, but, linear functionals or polynomials, yes, they are a perfectly good finite dimensional vector space. They are a vector space of their own, which means they have a basis. And if you can find 3 linearly independent linear functionals, then you can write all the other ones in terms of that, which is just mind-blowing to me, and I love it so deeply. So, for example, subbing in 3 and subbing in 2 are independent. Pretty sure. Could be wrong. I'm almost certain. And taking each coefficient separately, they're independent and they are a basis. And we've already done that. Yeah. You could have this basis, which is the one that, oh gosh, second. Yep, no, that's fine. So the phi1, phi0, which takes the constant term, phi1, which is the x coefficient, phi2, which is the x squared coefficient, and phi3, which is the x cubed coefficient. They are a basis for this. Every other linear functional can be written in terms of these. No, I don't know. I'll have to get to that. But that they are definitely a basis. And in fact, they will be the dual basis for something. Because the thing, there's no the dual basis. There's only a dual basis for another basis. Like every basis has its matching dual basis. So there is no standard dual basis, unless there's a standard basis, and in case there is a standard dual basis as well, but there is no, yeah. So this is a basis, but there is such a thing as a dual basis as well. And the dual basis has a property that I will have to look up. But I just wanted to talk about the fact that linear functions can be written that way, and it should be possible to make a basis entirely out of subbing in numbers, where one of the basis vectors is subbing in 0 and the other one is subbing in 10 and another one's subbing in something else. And it should be possible to make a basis entirely out of subbing in, differentiating and subbing in zeros. I'm almost certain that you can do that. So I have cool. So we do need to talk about a dual basis. So a dual basis, if you have a basis for V, then it has a basis as well. Then the dual basis goes for V dashed. And these are phis because the things in V dash are phis. They're linear transformations. Then the dual basis is chosen in such a way that when I do this function on that one, I get 1. When I do this function on any of the other ones, I get 0. So if you do phi I on Vi, you get 1. But phi I on Vj is 0 if I isn't equal to j. And you know that phi of one of these things is going to be a number. And so we're going to make it 0 and 1. And we've chosen this very, very carefully so that we can do what we used to do when we did the Gram-Schmidt process. So here's the idea. The idea is thus. I know that V, if V is in V, then V is equal to something times V1 plus something times Vn. I know this to be true. Sorry? That's okay. I know this to be true because this is a basis. And in fact, not just that, I know there's exactly one way to do this because that's a basis. Like a regular everyday spanning set, there might be more than one way to do it, but a basis, there's only one way to do it. There is a unique set of coefficients that will work. And the magic trick is that if you set up your dual basis in this way, then the correct coefficient in this spot is phi 1 of V. All the way up to the correct coefficient in this spot is phi n of V. So what phi 1 does as a linear functional is it tells you the coefficient of V1. And phi n tells you the coefficient of phi n, phi 2 tells you the coefficient of phi 2 when you write it according to this basis. Yeah. So this is the dual basis to the standard basis for P3. Because this tells you the coefficient of 1, this tells you the coefficient of x, this tells you the coefficient of x squared, this tells you the coefficient of x cubed. So you have this basis. That one, that basis, it's a perfectly good basis for P3. Then its dual basis is so the matching vector one here is the constant term. And this one is the coefficient of x. This one is the action of finding the coefficient of x cubed, x squared. This one is the action of finding the coefficient of x cubed. Because that's what the dual basis does. The function that the dual basis is, the first function in the dual basis is the function that tells you what the V1 coefficient is. Yeah. So I can only describe these functionals in words, but there are ways to do it. This would be phi of 0, not phi of 0, p of 0, right? This would be p dashed of 0. This would be p dashed of 0 divided by 2. And this would be p double dashed of 0 divided by 6. Because it's Taylor series, right? That's the constant term in a Taylor series. That's the x coefficient in a Taylor series. That's the x squared coefficient in a Taylor series. And that's the x cubed coefficient in a Taylor series. So the linear functional that does this to the px, like px goes to this, they are the basis for the dual basis. Yep, cool. Yep. Find a dual basis. Oh, can I write down part B? B, P2, R. I1 is I1 of f of t, the integral from 0 to 1 of f of t, I2. That of 0, cool, and find basis. I'm going to call them P1 and P2 and P3 instead of V1, V2, V3. so that phi 1 and phi 2 and phi 3 are its dual. Okay,
How do you have this?
cool. Okay. Based on timing, I think you can have your computer back now. But I'm not gonna. That is, oh, no, that's right. This is earlier than the normal ones because I have a meeting at 1. So. Okay. Okay, so this is the basis for R3. The dual basis will be the linear functionals that send these R3 to 0 to R. And so I know that writing something with these as the basis, the coefficients will be the linear functionals. That's the thing I know to be true. So I can think of at least 2 ways to do it. One is to find a formula based on ABC that will write the so if I have a vector x, y, z, and I can figure out what it is right, then the function that sends x, y, z to this, that's the first basis vector x. What's that? So the function that sends this to here is phi 1. And the function that sends this to here is phi 2. And the function that sends this to here is phi 3. And so if I could find this as a formula in terms of x, y, z, that would be it. So I literally could do it in a Maths 1B way if I wanted. And figure out the coefficient A in terms of x, y, z by doing row operations. I don't know if that's what the lecturer wants, but it will totally work. And in fact, that will literally be the inverse of this matrix, right? So they'll get down to the identity. Anyway, so, I could do row 2 is row 2 minus row 1. This is a very 1B way of dealing with this. So 0 minus 1, 1, y minus x. And row 3 is row 3 minus 2 of row 1. So 0, 1, minus 2, z minus 2x. And row 2 is row minus row 2. And row 3 is row 3 minus. Oh, I shouldn't have done that. Oh well, it's too late now. I could have just added them and made the 0 where I wanted. Whatevs. Row 3 minus row 2. So z is still there. We had that's going to be minus 3x plus y. And then row 3 is minus row 3. And we're so close now. I've got my third one now. I know that this is the third is phi 3. Should be minus it. Yes, you're totally right. Minus z plus 3y minus y. Yep. So that's my z3. That's my phi 3. Oh, that's an x. Yes. Thank you. You can tell I've done 2 revision seminars in a row and I'm wearing thin. And then I have just enough room, I think, if I pay attention. Row 1 is row 1 minus row 3, and row 3 row 2 is row 2 plus row. So I've got 0, 0, 1 minus z plus 3x minus y. So we've got 4x, so minus z plus 4x minus 2y. And we have x minus this, right? So z minus 2x plus y. There they are. They are my linear functionals. So I can say phi 1 yes. So phi 1 of x, y, z is minus 2x plus y plus z, and phi 2 of x, y, z is 4x minus 2y minus z, and phi 3 of x, y, z is minus is 3x minus y minus z. I may have made some mistakes, but you got the vibe. That's my first instinct to do that, but that's mainly because I spent all my life talking to maths 1As and maths 1Bs, and so the row operations are in my mind. Yeah, but you could theoretically have done this and said you need that phi 1 of 1, 1, 2 has to come out to 0, 1, right? And phi 1 of 0 minus 1, 1 has to come out to 0. And so you could have given this one names. So this would tell you that, so if phi 1 of x, y, z was like a x plus by plus cz, then this would be a plus b plus 2z, so plus 2c equals 1. And this would be that minus b plus c equals 0. And phi 1 of, what was the other vector? 1, 2, 0 is supposed to come out to 0 as well. And so that is a plus 2b equals 0. And this is enough information here to figure out what the ABC are that go with this one. Row operations. I mean, b equals c, you could sub that in there, and a is minus 2b, which is therefore minus, yeah. So you can figure it out. So we've got that b equals c, a is minus 2b, which is minus 2c, minus 2c plus c plus 2c equals 1. And so we've got that c equals 1. And so you've got 1, 1, minus 2. Yeah, there it is. 1 for z, 1 for y, and minus 2 for x. Way! Okay, and then you do that for all of them. Cool. That's fun. I mean, you know, relative to... That was not at all on the edge of this page. Okay. All right, so I'll give it a valiant attempt. My other question was, oh, I'm missing a whole page. Ah, that's 4. 5. Okay. So my other question was this. So find a basis P1, P2, P3 so that that is the dual basis. So I need to find some functions so that when I do this to each of them, I get zeros and ones. So I need P1 of x so that phi 1 of P1 is 1, and phi 2 of P1 is 0, and phi 2 of P1 is also 0. So this means that I need P1 dashed of 0 to be 0, according to this definition here, which means that the x coefficient is 0. And I need the integral from 0 to 2 of P1x dx to be 0, and I need the integral from 0 to 1 of P1x dx to be 1. And the integral from 1 to 2 of P1x dx should be -1. So hopefully this should be enough information to figure out the correct polynomial, and the easiest way to do that is to just call it a plus b. Was it P2? Yeah. So P1x, if this was a plus bx plus cx squared, then I know that P1 dashed is b plus cx squared, and P1 dashed of 0 is b, which is 0. So that I know. And so my P1 is now a plus cx squared. And I need the integral from 0 to 1 of P1x, the integral from a plus cx squared dx from 0 to 1, which is ax plus 1/3 of cx cubed from 0 to 1, which is a plus 1/3 of c minus 0, right? And this is supposed to be 1. But the integral from 0 to 2 of P1x dx is the integral from 0 to 2 of a plus cx squared dx, which will be ax plus 1/3 of cx cubed from 0 to 2, which will be 2a plus 1/3 of 8/3 of c, and that's supposed to be 0. And that's enough information to figure out what a and c are. So I've got that a plus 1/3 of c is 1, and 2a plus 8/3 of c is 0, and so that would be 2a plus 2/3 of c is 2, and so therefore I have 6/3 of c is -2, and so therefore c is -1, and therefore a is 4/3, and so therefore P1x is 4/3 plus minus x squared. Yay! And now I have to do that for the other ones as well. Etc. Sorry, that's just the first one, and now I have to do P2 and P3 as well. But P2, it will be that both of the integrals are 0. So not both the integrals. P2, the first integral, so the integral P2 dx will be 0. The integral from 0 to 2 P2x dx will be 1, and P2 dash 0 will be 0. And then with P3, the integral from 0 to 1 P3x dx will be 0. The integral from 0 to 2 P2 P3x dx will be 0. And P3 dash will be 1. Yeah, because they'll match up the other way. Ugh. But I can't see any other way of doing it than this. Yes, so the basis is P1x, P2x, P3x. Sorry? Yeah. And technically, it should be possible to write all, not that you want to do it, but technically, it should be possible to write all linear functionals from degree 2 polynomials as a combination of these three things. So for example, just subbing in 0, it should be possible to write it as a combination of these things. Because the dual basis works the opposite way as well. So the dual basis will, so if you want to write phi as some combination of phi1 and phi2 and phi3, then this will be phi of p1, whatever the linear functional is. And this will be phi of p2, and this will be phi of p3. So for example, if I had the linear functional on px that was p of 0, then I know that phi should be p1 of 0, phi 1, plus p2 of 0, phi 2, plus p3 of 0, phi 3. So to sub in 0 into any polynomial, I could integrate it from 0 to 1, integrate it from 0 to 2, and sub in 0 to the derivative, and that should tell me what the answer is when I sub in 0 if I put the right numbers in these spots. So we've already got this one. Phi 1 of 0 was 4/3, right? Because phi 1 had a 4/3 at the beginning, yeah? And so this will be what phi 2 of 0 is. This will be what phi 3 is. So the first step in subbing in 0 into any function could be to integrate it from 0 to 1 and times by 4/3, if you want it. Anyway, that's enough. My meeting's about to start, so I will stop there.